grab your circle, spin it round, spin that circle over town, down, 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 down. You hope you had a good Jamboree with your review packet. I think we already looked at the first set of answers yesterday. I guess if you missed them, there they are again. But here are the ones you haven't seen yet, 20 through 29. I guess we're missing 27 here at the bottom. Let me sneak that in. Oh, x equals 4. 27, x equals 4. Don't worry about the answers here for parts A and B. That was a separate worksheet that had some of those equations of lines problems in them. But hopefully you've now seen all the answers. Let's blast through. Here we have two angles that are both inscribed angles. I know this because their vertices are on the circle. And not only are they both inscribed angles, but if you pay attention, you realize that both angles are opening on the same arc. They're both intercepting the same arc. And so they're congruent for one thing, and they're both half of the arc, which is 66, 33, done. Number two, there were a couple of you guys who, from yesterday's response, told me number two was kind of one of the trickier problems. But you know, one thing with circle problems you always got to look for is diameters, because that's going to give you nice semicircles. And so, if I want to know, well, first of all, this is 54, right? And because of the congruent chords, that makes this 54 also. And the semicircle means that this has to be a diameter. We actually have a very specific theorem that tells us if your inscribed triangle has a hypotenuse that is a diameter, has to be a right triangle, right? But you could have also done, you know, 180 minus 54 to get this 126, then taken half of 126 to get 63. So you had a couple different ways, but you couldn't have done it without the diameter. Now, as far as this little guy goes, a little bit a simpler situation because it's a triangle made of two radii. The radii are always congruent to each other, right? So that makes him an isosceles triangle. So the base angles are congruent, and so you can see that I subtracted 54 from 180 and then just divided the remaining 126 by 2 to figure that both of those are 63s. And so you get answers of 63 for both of these, but for very different reasons. Number 3, we have diameter again. I always look for diameters. I really always look for those. Now, this inscribed angle is going to be doubled to get to the arc, and I'm just going to subtract that from 180 to get to F. This, once again, is a semicircle over here on this side too, right? Semicircle. So I'm going to subtract 48 from 180, and then I'll divide that angle by 2. I'll divide the arc by 2 to get to the inscribed angle. So, I think I did them in reverse order, but the answers were 66 for E and 122 for F. Maybe we actually fix those right now. Nope. There you go. All right. Number 4. I have an inscribed quadrilateral, so I know the opposite angles. The opposite angles are congruent. So, or I'm sorry, supplementary. Opposite angles are supplementary. Theorem 10.10. So I subtract 116 from 180 to get the 64 over there. That's how I got that. And then I'm going to double that angle, that inscribed angle, to get the arc. So this arc out here is 128. So now I can just subtract 165 from 128 to get G. Now what about H? Well, I think I'll use the 65 again to get H, because I have this 92 inscribed angle down here. It kind of has that shape, and so you can see the arc it's intercepting is actually this arc right here. So that has to be double 192, right? This arc has to be double 192, which would be 184. Whoops, there it is, 184. So now I do 184, subtract the 65, and that leaves what's left, H119. So using inscribed angles like crazy on a lot of these problems. Number 5 um, is, a problem that we have a nice theorem for it now, and it says that when you have two chords intersecting, the angles created, because I know that if this angle shown as 124, I know that this angle here is also 124 because of their vertical angles. And so those two angles um, are intersecting two separate arcs. This smaller one, this arc over here, this guy right here, this arc up here. And those two arcs, I average those arcs, I get the angle. That's basically what the theorem tells me, theorem 10.12, 1012. Okay. So that's what I did. I set up the relationship where I have one of the arcs is 78, the other arc is J. I average them, right, or multiply by 1/2, as the theorem says, and I set it equal to the angle, 124. So I multiplied by 2 and subtracted 78. I think that is the quickest way to get that answer. But you don't have to know that theorem. In the old days, um, what we would do is we would actually grab a new chord, kind of like this one right here, which creates two new inscribed angles that weren't there before. And then you can take, half of 78 to get this angle over here, so that would have been 39. And of course, K we haven't talked about, but K is just linear with 124. So what is that, 56, I think, right? And now I have this triangle, and I could subtract those from 180. And so that's 80, 90, 95 together. So this would be 85. And if you notice, now I could double 85 and get that same 170 for J that I had gotten using the fancy theorem. I think that particular method is more work, but it certainly is another way of working around it if you really had to. Okay. All right. Let's move to number 6. So a couple of you guys mentioned number 6 is the trickiest problem when you answered the question yesterday, and it's because you're missing the information you need, or not the information, but you're missing a segment. You need another segment. Now, the easiest way, well, first let me show you this one. Uh, this is related to one of our theorems. So if I extend, see, this angle is outside the circle, and it's definitely being created by a tangent line, but then this is not a secant line because it stops at the center, right? Secant lines don't have to go through the center, but this one actually does, and that's really nice because that's, it gives us a 180 semicircle. Okay. And then I can write, you know, this arc right here in terms of the little arc that I'm missing here. So if this is M, this arc would be, what would it be? It would be 180 degrees, the whole thing minus M. So let's go ahead and pencil that out. 180 degrees minus M. Okay. And then we can use that theorem I was referring to, 1013, to do the big arc minus the little arc divided by 2. Look what I did down here. Big arc, 180 minus M, minus the little arc, M is equal to, or divided by 2, or multiplied by 1/2, is equal to the angle, 28. So I multiplied both sides by 2. I combined the M's. I went ahead and subtracted the 180 and divided by -2, and I got 62. So M is 62 degrees for the measure of that arc. Okay. Um, and by the way, once you get M 62, then things get really easy because N is just inscribed within 62, so it's just half of 62. M is the hard part to get, and it's pretty simple. But there is another way of doing this, okay? And it's adding a different type of segment. In this case, we're going to add a radius. Because of the tangent line, I have a couple theorems that deal with tangent lines. One specifically, theorem 10.1, deals with radii drawn to points of tangency. They're perpendicular. So it creates a right triangle for us with this triangle right here. Right triangle. And so if one of the angles is 90 and one of the angles is 28, I can subtract from 180 degrees in the triangle and get that central angle is 62. Well, that's a one-to-one relationship with the arc. See, I got the same exact answer for the arc doing it that way. And then I can once again subtract, or I'm sorry, divide by 2 to get the inscribed angle. So both of these were tricky because both of them involved adding a segment, whether we extended the radius into a chord so that I had a secant segment and could use theorem 10.13, or whether I added a radius in so that I created a radius chord intersection, or sorry, radius tangent intersection, so I could use theorem 10.1. I had to add something. So those of you that voted for number 6 as the trickiest, I do not disagree with you. Number 7, there were certainly a couple of people that mentioned number 7, and these are tricky, but you just got to break down the inscribed angles as much as you can. Like for example, P is an inscribed angle right here, right? It intersects this big arc, right here. And so that arc is going to be double what P is and vice versa. But we don't have quite enough information. So here's where you really have to save yourself. Notice that this angle down here is 90 degrees, and that means this angle up here is also 90 degrees. Whoops. Here, I guess it's not written, so I'll draw it in for you. Right angle right there. So what that means is that you have a diameter. If I connected these two vertices right here, that has to be a diameter because 180, right? Double 90 is 180. Now you don't have to draw the diameter to just multiply 90 by 2 and get 180, but 180 goes from this point right here all the way around to this point right here. That's the 90-degree angle that's intersecting that arc. And so now I can do the 180 and subtract this 28 right here. See what's left. And 180 minus 28 is, excuse me, 152. So how does that help me? Well, now I know what this pink arc is, right? I didn't know what this pink arc was before. This pink arc is the 152 plus the 60 down here. That's 212. Half of 212 is 106. And once you get one of these two angles, P or Q, then the other one comes very quickly because we know the opposite angles of an inscribed quadrilateral supplementary, 7-4. And so there you go. So these are pretty common types of problems, and you really just have to kind of use those inscribed angles and check until you have enough information. And usually it's going to involve some subtraction and then addition to get some of the missing arcs. Number 8 was a couple people were confused by it. It's actually easier than you think. What you really have here are two isosceles triangles, okay? Because all radii in any circle are congruent, and so this is an isosceles triangle, and this is different, but yet still isosceles triangle over here. So the base angles are congruent. So R is just as you see right here, 180 degrees from the triangle minus the vertex angle, and then divide that by 2. Both of those angles have to be 49, okay? And apparently I didn't write it in, but trust me, 49. But over here we get confused because I don't have that central angle, right? But think how much I do have. I do have this part of the arc, and I do have this part of the arc down here. But notice the the parallel chords. Remember, we did the little bonus theorem that said when parallel lines intersect a circle, they intersect congruent arcs. How about that, right? Remember that little bonus theorem? And so what that means is this guy up here is also 67. And so now I can subtract the 3 arcs I have to find the 1 arc over here I don't have, right? Just subtracting from um, 360, 144. So once I know that this central angle is 144, I do the exact same work to get the base angles. I do 180 minus 144, I divide that by 2, and each of these base angles are 18 degrees. And I guess I have these in the wrong order. So, I guess we should probably fix that. There we go. All right, moving on. Number 9 was actually the question that most people voted the trickiest problem of the first 10. And so, look at this. Look at this going through the center. If it goes through the center, it's a diameter. That's 2 semicircles. Semicircle up here, semicircle down here. So I could get t very easily just by doing 180 minus 84 minus 64, and I get t is 32. Okay. Now, what that does is it creates an angle out here, u, which is the intersection of 2 secant segments. And Theorem 1013 tells us that I have to do the further arc, the bigger arc, subtract the smaller arc, and either divide by 2, multiply by 1/2. You can see I divided by 2. And 84 minus 32 is 52, divided by 2 is 26. So u is 26. That's not the only way you get that, though. I mean, it's the quickest way for sure is to use a theorem we already have. But you could also use triangles, right? We have a big old triangle here. And I have like an inscribed angle over here that is intercepting 64 plus 32, so that's 96. So that would make that 48. And this big old angle down here is intersecting, think about it, it starts over here and then wraps all the way around past the semicircle and then includes t. That's what that big angle does. So 180 plus 32 is 212. 212 degrees, and if I divide 212 by 2, I get 106. And so I could do 180 degrees in the yellow triangle, minus 48 minus 106, and I would also get 26. It's just another way of getting the same answer, right? So there's other ways of working around it, but boy, if you know your theorems, it's the quickest and most efficient way to get your answers. Last problem on the front page was another one. This number 10 was almost identical to number 5, where you have the 2 chords intersecting. And so angle V is going to be the average of the 2 intersected arcs, 32 and 86. And that's what I show right here. I averaged those and got 59. And then once I know that V is 59, I can use linear angles to get W. And once again, if you didn't know this, you could very easily have added a chord right here, and then you could have said, half of 32 is 16, so this angle here would have been 16. Half of 86 is 43. This would have been 43, and then in this triangle, I could have done 180 minus 16 minus 43, and I still would have got 121 for W, and then I could have got V using linear angles. So another way that it could have been done if you really needed to. That brings us to the next page. And I didn't expect a lot of questions on this page because it was mostly pretty straightforward stuff. 2 pi r for circumference, right? 2 pi r. Don't approximate means leave it in terms of pi. This time they wanted you to use 3.14, and the diameter was 29, so instead of 2 pi r, we'll use pi d. So pi d is diameter 29 multiplied by about 3.14, so 91.06. Number 13 is one where we have to work backwards. They gave us the circumference, so I just plug that in into the circumference formula and divide by pi and divide by 2, and I get 41, so 41 feet. Number 14 gave me the circumference again. This time though, because they asked for the diameter, I mean, I could solve for radius and then double it at the end, but why not just solve for diameter directly? So I just set 30 equal to pi d, and then I divided by pi. Now, I would have divided by 3.14 and gotten a decimal approximation, but they did tell me not to approximate, so I didn't. Okay. Number 15, um, we get into arc length, right? So arc length is a fraction of the circumference. So we're going to take the degrees or measure of the arc over 360 and multiply by 2 pi r. And that's usually the way I do it. Some of you guys I know like to use the proportions, and that's fine. That's fine too. You can do the measure of the arc over 360 is equal to the length of the arc over circumference, and that works also. It told me that right here the radius is 12, so I plugged 12 in for radius, and the arc was 100 degrees, so I plugged 100 in for measure, and then you can see I reduced the fraction, multiplied 2 times 24, 2 times 12 to get 24, and then it said not to approximate, so I'm just going to leave it as 20 pi over 3 is as far as I can reduce it. And now if you did 6.67 pi, it's fine, except 6.67 is a rounded off fraction, right? 6.6 repeats forever, so it's better to leave it in terms of an exact fraction. Number 16, what is the length of FG? No, they gave you the length of FG, I guess. They want you to solve for the radius. So we're going to use the same formula but work backwards. So I plugged in the 150 here, I plug in the arc length here, and now I'm ready to solve. 150 over 360 reduces to 15 over 36, which reduces all the way down to 5 over 12, I guess. And then when you multiply it by 2, it reduces down to 5, 6. So I multiply by the reciprocal to get rid of that fraction right there. And I got 72. 6/5 times 60 is 72, which is your answer for that problem. Number 17. Um, this one, a couple people said they were stuck on, even though I just asked for problems from 1 through 10. But we have to find some arcs here. So like arc CE up here is going to be 90 because that's twice 45. And then I can subtract 90 and 125 to get arc CD over here is 145. So now I know my arc is 145. And they told me in the diameter, they said, use 35. Now, they told me to use 22 sevenths for, there it is, for pi. Now, why would I do that? Sometimes they do that. It's not exactly pi, but if you notice what 22 over 7 is compared to what pi is, they do round off to 3.14. So 22 over 7 is the first fraction that you can find that actually rounds off to pi to 2 decimal places. Now after that, they're different, but still, it's pretty close to the hundredths place. And so when I plug in 22 over 7, it actually works nicely because 35 over 7 reduces just to 5, and then when I multiply that by the 22, I get 110. And then the 145 over 360 multiplies by 110 to give me the final answer of 44.3. And really, I don't think that's exact. I probably should have said it's an approximation, but that's that one. So that's 18. I'm looking for this this angle here, and they gave me the diameter and they gave me the arc length. So I'm going to plug the arc length in for L. I'm going to plug the diameter in for D. I'm using pi D because why use 2 pi R if they gave you D? And then I need to remember one thing. This is what caught a lot of you guys on the last quiz. This is an inscribed angle. So the arc is not the same measure as this angle. The arc would actually be double that. It would be x, 2x. Okay, so that's why I put 2x in for the degree measure. And then it's just some algebra. The 2 over 360 really is just 1 over 180. And then when I do 20 over 180, it reduces all the way down to 1/9. So this big mess right here reduces all the way down to just 1/9 times x. And the pi's, by the way, had already canceled. I think we got rid of these pi's. And then I just multiplied side by 9 and get my answer, 54 degrees. Now, this is the same deal except using that proportionality way. You can see we still plug in 2x, we still plug in 6x and pi over 20 and reduce the pi's and then cross multiply. It's about the same amount of work. Some people like the proportions better, so go with the proportions. Now, you could have solved this, like what if I had just called this a w, solve for w? That would have been fine. You just have to realize that when I would have solved, if I got my answer at the end, it wouldn't have been 54, it would have been 108. It would have been the arc, and they were asking for the inscribed angle, so I would have had to divide by 2 at the end. That's why it's a little safer to just double it at the beginning so you don't forget. The application problem, so you're driving around a circular track, you go around twice, and it takes you 4 minutes and 48 seconds. We want miles per hour, so I converted your 4 minutes and 48 seconds into hours for you, 0.08, but hopefully you remember how to do that. 2 laps took me 4 minutes, so that's 4 times 60 seconds plus another 48 seconds, so that's a total of 288 seconds. Whereas an hour is 60 minutes at 60 seconds, or 3,600 seconds. If you do 288 divided by 360, that's the fraction that gives you 0.08. Okay, so speed is equal to distance over time, and we just found that the time, or you were given the time, is 0.08. What is the distance? Well, the key is that we're doing 2 laps here around a circular track. Once around a circular track, I think we just call circumference. So we're just trying to do 2 circumferences. So here we go. The circumference is 2 pi r. 2 circumferences is 2 times 2 pi r. By the way, they told us the radius of this track was 0.8 miles. So we're going to plug in that 0.8, and they also told us to use 3.14. Okay. Well, maybe they didn't specifically say it, but if I don't, I'm not going to get an approximate value that I can really comprehend. So I have to throw that in. And so 10.048 turns out to be the distance of 2 circumferences. That's how far I drove 2 times around the track. So that's my distance. So now I have distance over time. And when I divide 10.048 by 0.08 hours, I get a fairly fast answer of 125.6 miles per hour. All right. Last page. This guy right here had these 2 chords intersecting, so I know the average of these arcs is equal to that angle inside, 115. So that's what I did. I did the 105 plus the x multiplied by 1/2 equals the 115, and I solved it by multiplying by 2 and subtracting 105. Number 21. This is the first time I think that we've seen theorem 10.1, which tells us that when a tangent intersects a chord, the angles formed are half the intercepted arcs. So you could either have taken 234, divided it by 2 to get this guy, and then use linear angles, or subtracted the 234 from 360 to get this guy, and then taken half. Either way, 63 is the answer. 22, this is the intersection outside. So this is theorem 10.13. It's big arc minus little arc divided by 2 or multiplied by 1/2. So the one problem here is, you're trying to find this angle, but I don't have this arc right here either, right? And so at first you're like, how am I going to do this? But remember, there are 4 total arcs on this circle that must add up to 360. So if I do 360 subtract 95, 85, and 175, I get 5. So that's where this 5 came from right here. By the way, 80 divided by 2 is 40. 21. I'm sorry, 23. We got another one just like we saw. Angle is outside, so I'm going to use 1013 again. Big arc minus little arc. This is probably a real dangerous problem for a lot of you because you're going to forget when you subtract to um, to distribute, you have to subtract both parts. So I get a +2, not a -2. If you made that mistake, you did not get 7. Okay. Also, some of you guys do not use parentheses when you're multiplying or subtracting these binomials, and that's going to get you in all kinds of trouble. But once I get it set up correctly, I just multiply each side by 2, so that's nice. And then I combine like terms. I guess I could have done that first step. Subtract 8, divide by 10, and sure enough, you do get 7. So if you need to look at this work for a little longer, freeze this slide. 24. Now we're into the segment length theorems. So that's 10, 14, 15, and 16. This is 10, 14. When two chords intersect, the segments of each chord, when multiplied, right, equal each other. The products of the segments are the same. So 8 times 3 is going to be equal to x times 6. And that's what I set up over here. And so it's a pretty simple problem once you set it up. 25. So this is now theorem 1016. When a secant and a tangent intersect outside of a circle, the secant segment, so that's the whole thing, multiplied by its external piece is equal to the tangent segment squared. So notice that's exactly what I set up here. The external piece was x. The entire secant segment, right, is x plus the 8. And then the external part, or I'm sorry, the tangent segment is 3. So I squared that. It's quadratic, so I set it equal to 0. I felt like some of you guys were starting to get better at this based on what I've seen coming out of quiz 3, but some of you guys still struggling with quadratics. I just want to remind you that the algebra review video on quadratics and polynomials is still available. It's long, but you can just watch the parts that you need, and that might be helpful. By the way, after I factored it and found my answers, I did have to throw out the -9, right? Because we can't have a distance of -9. 26 was almost the same theorem, except it was 1015 instead of 1016. And so it was two secant segments. And so this time I had to do external times whole thing is equal to external times whole thing. A lot of you guys just, I think, do external times internal because it looks, that's kind of what you do with the chords, is part by part, but it's not that. It's not that way. It's whole thing times external. It is a different relationship. So the external is x plus 1. The whole thing is x plus 1 plus 5, or x plus 6, right? The external is x. The whole thing is x plus 8. So once you have it set up, it's all algebra. Geometry is just setting it up. Algebra is the rest. So I FOIL out this one, and I got x squared plus 7x plus 6. I distributed the x up there. That's why you got to have those parentheses, x squared plus 8x. And holy cow, those x squareds drop out. I don't even have to solve a quadratic. I just subtract 7x and I'm done. X is equal to 6. Number 27 is back to theorem 1016. So that's going to be external times whole thing equals tangent squared. So x minus 2 is the external. What is the whole thing? Well, it's x minus 2 plus x plus 2. Well, x plus x is 2x, but the 2's cancel, don't they? So we just get 2x. And then the tangent segment is just x, so we square that. So let's go do the math. When I do distribution here, 2x times x is 2x squared. 2x times -2 is -4x. I subtract the x squared over, so now I have x squared minus 4x. This is actually a really easy factorization. We don't have to do like a trinomial and the binomials, but sometimes people kind of, it's like too easy, and then they kind of freak out. So check this out. If I had like, 5 times x plus 2, I could distribute that and get 5x plus 10, right? Well, if I was going to factor that, I would say, what do these have in common? Well, they have a 5. And I could subtract or divide the 5 out, factor the 5 out. So this is called factoring out a common term or factoring out a monomial. It's reviewed in that same algebra review video that I just referenced. So you can check out the factoring review part of that. That's what I did here. Both of these two terms, had an x in them. And so all I had to do was to factor the x out. Now I can use the zero product property because I'm multiplying x times x minus 4 and the answer is 0. One of those things has to be equal to 0. So what makes x equal to 0? 0. What makes x minus 4 equal to 0? 4. And we had to throw the 0 out because you can't have a 0 distance or a negative distance, which you would get if you tried to plug the 0 in there. Okay. All right, almost done. 28. There was a typo. A couple people asked about it, but yeah, it's not supposed to be two x's. It's just supposed to be an x and a y like normal. So sorry about that. So the formula for a circle is this right here. I'm going to go ahead and steal this, bring it over so we can take a closer look at it. So HK is going to be your center. Notice it's x minus h, not x plus h, x minus h. Okay, so what that tells me is that when I see this plus here, that had to be created by a double negative, and that means that your h is actually -7. Whereas your y minus 4, the 4 was just plugged in directly. It stays minus, so the k value is just 4. So your center is at -7, 4, and your radius is not 2 because that's r squared, right? That's r squared, not r. So I'd have to take the square root of 2, which is square root 2, to get the radius. If you approximated that to 1.41, that would be fine, except it did say equal here, so probably you just left it as root 2. Last problem, same equation, but this time I'm plugging in to write the equation. So I'm going to have to plug in a -1 for h and a -3 for k and a 5 for the radius. So this turns into a plus, and this turns into a plus, and this turns into a 25, doesn't it? And then I can graph it by just going to back 1, down 3, and then in each direction, because the radius is 5, I would go out 5 units to find the points on the circle. 1 there, 1 there, up 5 for another one. Once you have those points, it's pretty easy to draw the circle through them. My circle, of course, popped up before I even unloaded those points, but that's the last problem. So now your halfway circle reviewed. You have another review packet starting today. Work ahead as far as you want, so you can ask questions if you need to. And help session at 2 o'clock today. Hopefully my internet will be a little more functional and we can go back to Meet, but I'll try to help you even if we have to use Jamboard again. Have a Thursday.